As we have studied from earlier slides, frame relay consists of many logical connections, and these logical connections can be deployed in different topology. Now, one of the deploying method for our frame relay connectivity is what we call fully meshed connectivity, whereby we have circuits connecting to every site, like in this. Now, one of the advantage of this method is that you have full redundancy. Now, but of course, the disadvantage is it's very expensive to implement because you need to have circuits to every locations. Now, in the real world, the more practical, cost-efficient solution is the hub and spoke deployment, whereby all the remote sites have one connection to a centralized hub, and so that all data is flowing to the hub or through the hub to reach other remote sites. So one of the advantage of this hub and spoke deployment, it is cheaper to deploy compared to a fully meshed deployment. But the hub and spoke topology does has its disadvantage in that it has a single point of failure, which is the hub. So if the hub fails, all the remote sites will not be able to communicate with each other. So a full mesh or a hub and spoke deployment, it's the two extreme way of connecting the frame relay sites together. Over the years, a hybrid methodology is being introduced, whereby the more important sites, such as your data center, will have fully meshed connectivity, where the less important sites, like your branch office, for example, will have hub and spoke deployment. We call this hybrid method partial mesh. Now, as we have mentioned, hub and spoke deployment is the most common way of deploying frame relay connectivity because it is the most cost efficient way of deployment. But using a hub and spoke topology does create some reachability problems. We'll talk about this problem and see how we can resolve this problem. Now, in the beginning, all the circuits of these three remote sites are reporting to the same S0 interface. Now, as routing updates are coming in from the S0 interface, let's say from site A routes are not being able to advertise out through the same S0 interface, even though the objective of this backflow is so that you want to advertise site A routes to other sites. This routing U-turn is not allowed because frame relay practices the concept of split horizon. And split horizon says that the route coming in from S0, one interface, will not be allowed to flow back the same interface. So even though you are trying to reach other circuits through S0, not going back to the same circuit, split horizons doesn't see the difference. So long as you're trying to reach back the same interface, split horizon will prevent your routing updates from being sent back. So as such, all the remote sites will only be able to see their own routes and the HQ routes. They will not be able to see each other's remote routes because of the split horizon happening at the S0 interface here. Now, to overcome this limitation, what we can do is of course turn off split horizon, but then if you do that, if there's any routing loops, you have to bear the consequences. So rather than turning off split horizon, we try to find ways around this split horizon rule. So what we did was, the S0 interface has been subdivided into a lot of sub-interfaces like this, and each circuit reports to a different sub-interface. So now the routes coming in from site A is coming in from S0.1. So if we want to advertise the route to other sites, such as site B and site C, it will use different sub-interfaces to advertise the routes out. So as such, the split horizon will not stop the routes from coming in from S0.1, and then it will not stop the route from going out of S0.2 as well as S0.4 to reach the other remote sites. So using this sub-interface method, we are able to work around the split horizon rule. So at the end of the day, all the remote sites is able to learn all routes, not just the HQ routes. It's able to learn everybody's routes, including each other's remote site routes.